So what even is this thing? What does it mean to raise e to the power of some matrix? In other words, what does it mean to exponentiate a matrix? Well, I'll get into what that means. If you recall the Taylor series for e to the x, and you remember from your calculus 2 days or wherever you learned Taylor series that this is true for scalar x. But it turns out it's also true for a matrix input A. So if we have a square matrix A, we can take e to the power of that matrix and throw it in our Taylor series. However, it still seems a little ambiguous. Like, how can we calculate something like this? What can we do to make this easier for ourselves to calculate? And it turns out that this Taylor series can simplify super nicely if we make the assumption that A can be diagonalized. So diagonalization means that A can be written as P dP inverse, where P holds the eigenvectors and D holds the eigenvalues of A. So the eigenvalues of A are in the diagonal here. We have zeros on the off diagonal. And so what we see in this matrix definition of e to the a, that we want to raise a to some power n. So let's start taking powers of a and see what we get. So first we have a is equal to PDP inverse. So let's multiply a by a. So we have p d squared p inverse. And you can do this for a cubed, a to the fourth, a to the fifth, and you'll find that a to the n is equal to p d to the n p inverse. So this is great. We can substitute this directly into our exponential Taylor series for a square matrix A. So e to the a is equal to, I'm just writing what I have in the blue box, and we can substitute this diagonalization into our sum. This sum only depends on n, which means that we can take p and p inverse and take them outside of the sum. And so we get something that looks like this. And you might notice that this is just the definition of, this is exactly equivalent by the Taylor series, e to the d. So we have e to the a is equal to p e to the d p inverse. And this is good and all, but this is like when you look up the definition of something up in the dictionary, you're like, okay, what's e to the a? And it's p times e to the d. Or we kind of have the word that we're searching up that's in the definition, so it's a good start, but there's like a cyclical argument, and we want to further analyze this and see if we can make any further simplifications, and it turns out that we can. So
e to the d is equal to this Taylor series.
And so what we can do, we notice that d, it's just the eigenvalues of a in the diagonal, or whoops, that should be a lowercase n, and zeros in the off diagonal. And if you notice, each one of these matrix elements kind of looks like an identity matrix. And what I mean by that is that an identity matrix has ones in the diagonal and zeros in the off diagonal. So it looks very, very, very similar besides the diagonal portion of D. So how can we make D sort of look like I? Well, what we could do is we can define a matrix element. I'll call it capital lambda of I sub j. So this is just the elements of D.
So D is filled with a bunch of lambda sub ij's.
And this is equal to, we'll define this to be the eigenvalue of the ith row, and then times the Kronecker delta. And you see, if you take the case where I is equal to j, the Kronecker delta goes to 1. You have lambda sub I is equal to the eigenvalue. But if you take the case where I does not equal j, then the Kronecker delta goes to 0. And this represents our diagonals of D, and this represents our off diagonals of D. So we've successfully written it in terms of a matrix element. By this definition here, the matrix element capital lambda sub I is the same thing as the ith eigenvalue. So we can rewrite D with the zeros in the off diagonal. I mean, these are technically still capital lambda terms, but they go to 0 because I does not equal j.
So as you can see, this sort of looks like an identity matrix.
So I'm going to do a very sneaky trick. I'm going to sort of factor out the lambda matrix element term. So I am going to do this. I'll pull out a lambda sub II, and you see we get an identity matrix. So D is equal to capital lambda sub II times identity. What we can do even further is we can substitute this definition for D, let me box it, into our Taylor series definition for e to the d up here. So we're going to substitute it into that. So let's write the first couple terms of e to the d. And let's substitute in d equals capital lambda sub I times identity, and we get the following. And a nice thing that we know about this is we can actually factor out the identity matrix, because a nice little property of the identity is that I to the 0 is equal to I to the 1 is equal to I squared is equal to so on. So I is equal to powers of itself. So this is just all equal to I. So we can just factor it out. So we have e to the d. But also you might notice by Taylor series that this is just a scalar exponential. So e to the d is equal to I e to the lambda sub I. And we can rewrite I as just, as I said, 1's in the diagonal and 0's in the off elements. And this is multiplied by
e to capital lambda sub I.
So we can substitute this in. So e to the eigenvalues of A are in the diagonal and 0's are in the off diagonal. And so this is e to the d. And we said that e to the a, so e to the a
is equal to
p e to the d p inverse. And so we can finally substitute e to the d into here for our e to the a, which is what we wanted to find. We finally get e to the a is equal to p times e to the d, which is just this that we just found out, times p inverse, and we are done. And you might think, well, what are even the practical applications of this? What can I do with something like this? Well, it turns out that in quantum mechanics, you have something called the time evolution operator, which basically tells you how the states of a system change from some initial state over time. And the Schrodinger equation for that system looks something like this, where we have e raised to the power of something, and it turns out we have e raised to the minus I times capital H over h bar, and capital H is the Hamiltonian, and the Hamiltonian in this case is a matrix, so it's a matrix. So you can't really do the time evolution operator without doing exponential matrices, and that is why they are useful. Okay, here's a quick example of how you can find the exponential of a 2x2 matrix. So we know that the cookbook recipe for finding e to the a for an invertible a is as follows. And I'll leave this as an exercise for you guys, but the eigenvectors and eigenvalues of a are as follows. And so we can assemble our P matrix using these eigenvectors v1 and v2. And we can also find the inverse of P, which ends up being this if you do the computation. And so now we can plug everything into e to the a. And once you do all the computation, you should get